So we are on this slide already. So I'll go back to the note here. So note solution concentration may be expressed as mass of anhydrate over mass of solvent, or as mass of hydrate over mass of free solvent. And the choice affects the value of S and the relative supersaturation value phi. Okay, so most of the time, class, is mass of the hydrate over mass of free solvent, but it could be mass of the anhydrate over mass of solvent. So the problem anyhow specifies the unit of the concentration of your solution. Okay, to illustrate the use of the three formulas or expressing the concentration of your solution, the degree of concentration of your solution, that is, we'll go to this sample problem. So by the way, these sample problems are taken from Colson. The sample problems I'm using in this slide are all coming from Colson. The sample problems available in McCabe and Jan Kuplis will be left to you to read because they are easy anyway to understand. I have already read through all of them. So for sample problem number 1, you are given at a temperature of 293 Kelvin, a supersaturated solution of sucrose containing 2.45 kilograms sucrose and kilograms water. If the equilibrium saturation value is 2.04 kilograms sucrose per kilogram of water, what is the supersaturation ratio in terms of kilogram sucrose per kilogram water and kilogram sucrose per kilogram of solution? So I will deviate from this particular slide, class, and I will go to the board. That way I can write down the given information. I will just speak from each of the sentences, the given information, but I will not anymore share it so that we can save time. So I will stop sharing from this and I'll go to the board where we can use ours, which we can use as, I can find the board. Wait, class. Okay, that's it. So for our first sample problem on crystallization, we have the very simple problem of the application of determining the supersaturation ratio and kilograms of sucrose per kilogram of solution of your given supersaturated solution of sucrose in water. So we will have, based on the statement, I will read it and then write the information on the board. That way we can go directly to the use of the formula. Wait, class, I still need to admit. Okay. Now, at 293 Kelvin, a supersaturated solution of sucrose contains 2.45 kilograms sucrose per kilogram of water. So we will now go to the board and see what we have there. We can write what we have already, what I have already read. Okay. So this is for our sample problem number 1. 293 Kelvin. And a supersaturated solution having 245 kilograms sucrose. Concentration, which is 200 or 2.45 kilogram sucrose per kilogram water. So this is the concentration at this temperature. Then we have on the next line, the equilibrium saturation value, which is 2.04. So if it's equilibrium concentration value, that would be your C asterisk, and that would be 2.04 kilograms sucrose per kilogram water. Okay. So far, I think these are the three information we can work our way through. What is the supersaturation ratio in terms of kilogram sucrose per kilogram water? So required.
Miss, excuse me, miss. Nang
Yes.
wala ga share ang screen, miss.
Ay, sorry. My goodness. Siri lang ko sulat. Sorry. Do you see it now?
Yes, miss Arna, miss. Thank you.
Okay, so this is the initial information given in the problem. At 293 Kelvin, the concentration of your supersaturated solution is 245 or 2.45 rather kilogram sucrose per kilogram water. The equilibrium concentration is 2.04 kilogram sucrose per kilogram water. Okay, we are required for the supersaturation value in kilogram sucrose per kilogram water. And what is the supersaturation ratio in terms of kilogram sucrose per kilogram water and kilogram sucrose per kilogram solution? Wait. So the other one is kilogram sucrose per kilogram water. Well, this one is kilogram sucrose per kilogram solution. Okay, so this is what the problem is asking from us. So if we go back to the slide as to the formula, so I'll just still share to you the board, that way I will not be forgetting where am I. So the formula in determining the supersaturation ratio for S is C over C asterisk. So I will write it there. So you have S is equal to C over C asterisk. Okay. Now, in both letter A and B, we are to determine the supersaturation ratio. But in A, it should be kilogram sucrose per kilogram water. And in B, it should be kilogram sucrose per kilogram of solution. So we'll go to the next slide to do that. So if we will have S, letter A, being equal to C over C asterisk, meaning you will determine the S, the supersaturation ratio, based on the original units that are given to you in the concentration. Excuse me. So if you're going to look at the concentration units, they are in kilogram sucrose per kilogram water. So you're going to determine here the supersaturation ratio based on these original units. Okay, in letter B, there's a change. So what we're going to do, we will simply have a case of simple substitution. So we will do that. That would be 2.45 over 2.04. So you have here a 2.45 over 2.04, because the unit of these two is kilogram sucrose per kilogram water. This is also kilogram sucrose per kilogram water. It doesn't mean, class, that your supersaturation ratio has a unit of kilogram sucrose per kilogram water. It means that you're only going to determine the supersaturation ratio based on the units of your concentrations having kilogram sucrose per kilogram water. Doesn't mean that the unit of this is kilogram sucrose per kilogram water, because if you look at it, it doesn't have any unit, because the units anyway will just cancel each other. So in this case, you will have a value which is 1 point something. Wait. So you have a 2.45 divided by 2.04. So that would be a 1.20. That would be a 1.20. Now, letter B. Okay, in letter B, this time the unit that the problem is asking from you is when you determine the supersaturation ratio would be kilogram sucrose per kilogram of solution. How will you do that? And somebody suggests to me, how will I find the supersaturation ratio wherein the units of these two, the C and the C asterisk, has to be kilogram sucrose per kilogram of solution? What will I do?
Maad kami is 1 kilogram sa kada C.
Okay, so I will first have a C computed and UC computed. This is 2.45 kilogram sucrose per kilogram water, right? So what do I do? Kilogram sucrose per kilogram of solution. So what do I do now? I'll erase. I need to convert to unit kilogram sucrose to kilogram solution. What do I do? My C, sorry. Would it be adding 1? Would it be adding 1? Simply adding 1, that's it?
Ang denominator gali miss dapat ma-add ka 2.45 sa dalom. 2.45 sa dalom ma-add ka.
Okay. This is what was that, Joburn? Is that you, Joburn? Was that Joburn?
Yes, miss.
Okay, so C will be equal
Ma-add kami 2.45
kilogram sucrose. Remember that this is for every kilo of water. So what Joburn is saying is this should be now kilogram water. This is 1 kilogram water, right? Plus what?
plus kilogram of sucrose miss which is 2.45 para masolusyon sa miss.
So hindi ka mag-add lang 1 sa denominator, but rather it would be the sum of 1 and 2.45. Where do we get this from? It's because of this. For every 2.45 kilograms sucrose, you have 1 kilogram of water. So the total of the two must be the sum of 1 kilogram water and 2.45 kilograms sucrose. Your numerator is still 2.45. So this would be your new C. So a 3.45 and 2.45 divided by a 3.45. That should be a 0.71. Okay? Then you will do the same with your C asterisk. Your C asterisk would be a 2.04. I will not anymore place in the unit, but divided by 1 plus 2.04. So in this case, you have a 2.04 divided by a 3.04. So that would be a 0.67. And now you have, in letter B, a supersaturation ratio, which is now using a different unit for the C and the C asterisk. And that would be, what would that be? 0.71 divided by 0.67. 0.67 times 0.71. So that would be a 1.05. So this is your degree of supersaturation based on the unit kilogram sucrose per kilogram of solution. Not that its unit is kilogram sucrose per kilogram of solution. Okay? So that's in the case of the first sample problem we have discussed. So we go to sample problem number 2 if there aren't any more questions on this. I'll stop share. I'll share. Okay, so that's our sample problem number 1. Okay, we go to sample problem number 2. Now, before we go to sample problem number 2, we need first to understand the different variables representation of the properties of our streams in our vacuum crystallizer. So for the feed, we have F, and for its mass fraction, we have XF, HF for its enthalpy, TF for its temperature. For the vapor, we represent it as V. Its enthalpy will be H sub V. For the magma, we have it represented as capital M. Correspondingly, these are how we represent its concentration, its enthalpy, and its temperature. The mother liquor is L and the crystal is C. They both also have the XL and the XC, the concentration in terms of the solid content and the enthalpies. You need to understand the representation of the properties and the variables for this, because in the next problems you will be using some of this. Now we go to the crystal yield. Okay, so the yield of crystals produced by a given degree of cooling may be estimated from the concentration of the initial solution and the solubility at the final temperature, allowing for any evaporation, if there is, by making solvent and solute balances. If I will simplify everything that is stated here according to what is stated, you can determine the crystal yield by making solvent and solute balances. So that particular process will be illustrated to you in the next slide. So if we do material balance based on the solvent content, that is, we have, this is omega 1 being equated to omega 2 plus y times r minus 1 over r plus omega 1 e. This is a formula from Coulson because we don't have this formula in Gen-Kuplis, neither in McCabe. So we'll define first what is omega 1, omega 2, E, Y, and R. I think you know already what Y is. That's the yield. But let's define, or let's know what W1 or omega 1, omega 2, R, and E represents. So your omega 1 and omega 2 are the initial and the final masses of solvent. So take note of solvent in the liquor. Y is the yield of crystals. R is the ratio. Ratio of what? Molecular mass of the hydrate over molecular mass of the anhydrous salt, meaning the molecular mass of the solid with the water divided by the molecular mass of the solid only, not containing the water because it's anhydrous here. And E is the ratio, the mass of the solvent evaporated over the mass of the solvent initially present in solution. This equation here allows us to account for the solvent initially present in our feed to the solvent that is present after crystallization already proceeded, to the yield, and to this E, the amount of solvent that is present in the evaporated water. So anyway, it's defined here. E is the ratio of mass solvent evaporated over mass of solvent in initial solution. So this is our solvent balance. What about the solute balance? It says we have to do both. That way we can come up with the yield. So this is our solute balance. The C1 and the C2 are the initial and final concentration of the solution. Take note, how is it expressed? Mass of anhydrous salt over mass of solvent. Meaning, your concentration here should be in the form solid only over solvent. Concentration in terms of the solid content only over the solvent. Now, if we will substituting omega 2 from equation 1, meaning class, I will get an expression here of omega 2 from this equation and substitute it here in this equation, we will arrive at this new equation. The omega 2 derived from the solvent balance in equation 1 will be substituted to this particular equation of our solute balance, and it will giving us this particular equation. If we will solve this in terms of the yield Y, it would be something like this. Okay, However, the E has to be first determined if it is not given in the problem. If the problem already gives you the amount of water evaporated and the initial amount of water, you have no problem. The two equations that we have dealt with, equation 1 and equation 2, and equation 3 simplified will give you this particular formula. Now, the equation, this very long equation here, allows you to solve for the amount of water evaporated per unit mass of water present initially in the solution when it is not given. So meaning you only have to worry about this formula if it's not in the first place stipulated in the problem. What is this E? Actually, it's easy. Solvent evaporated over solvent initially present. But if it's not given, as I said, you have to know how you will determine it. And it has this very long formula in the process of determination, in the process of determining it. So in this formula, the lambda that you see is the latent heat of evaporation of your solvent, referring to your water. And since again, it's stating about lambda, or latent heat of evaporation, you will be needing here the temperature. That way you can read this out. You can read this out from the steam tables because most of the time our solvent is just water. Your Q is the heat of crystallization of the product. This one class has to be given by the problem. We can't find this anywhere. It has to be the problem that has to give this, or either the problem will give us this and all the informations in this formula and only this unknown. We can do that. But if it is E that you want to know, this has to be given by the problem. Your T sub 1 is the initial temperature of the solution, meaning of the feed as initially processed in the crystallizer. And T sub 2 is the final temperature of the solution. The solution that is inside the crystallizer, the same solution, the magma, that is dispensed by your crystallizer and later on separated into crystals and mother liquor. So T sub 2 is your final temperature. Cp is the specific heat capacity of your solution. If Q has to be given by the problem, the specific heat capacity of your solution, which is dependent on its solid content, has to be also be given. Otherwise, it's impossible for us to determine the amount of water evaporated per water present in the initial solution. So again, you will only worry about this formula, that is if it's not possible in the problem to just simply by algebra or simply picking it out in the statement the value of the E. So this is the yield. So our main goal here is that you will have a formula of determining the yield of crystals in an adiabatic or vacuum crystallizer, which is often the case used in the industry. In the case of the sugar central, we have a simple naturally exposed cooling process for our crystals, and that is in the crystallizer. It's open and it's not under vacuum. It's a simple process of cooling. Question, will we be using the same formula even if the process is not under vacuum? As long as it is adiabatic, you can still use this particular formula. If the problem is silent rather about it being adiabatic, then assume that it is adiabatic. That way you can solve for the yield. Now, Janko places a different process or a different material balance, but it's simple, very simple. That is why I'm leaving it to you to read and how to determine the yield of crystals. I'm using this particular source because it's a different approach than the one you have in Janko Please and McCabe. And most of the time, problems in the board exam are taken from Colson. So that is why I'm using Colson now for the topic of crystallization. So this brings about our second sample problem, which is our application to the formula shown to you a while ago. So what is the theoretical yield of crystals which may be obtained by cooling a solution containing 1,000 kilograms of sodium sulfate with this molecular mass in 5,000 kilograms water to 283 Kelvin? The solubility of sodium sulfate at 283 Kelvin is 9 kilograms anhydrous salt per 100 kilograms water. And the deposited crystals will consist of the decahydrate with molecular mass 322 kilogram per kilogram mole. It may be assumed that 2% of the water will be lost by evaporation during cooling. So since the problem already stated in the last statement that it may be assumed that 2% of the water will be lost by evaporation during cooling, then that simplifies the problem for you because this is already your E. Amount of water evaporated over initial amount of water. That's actually the percentage of water evaporated from the initial amount. Then you don't need to worry about finding the E based on equation number 4. Excuse me, this particular equation because it's already stated here. Okay, so I'll go to the board and write down what we can identify as the given information in this problem. So number 2. For the given in number 2, I will read out and then please listen. My memory is very short term, so I might forget what I read. So in the first statement, it says that, wait class, where is that? Okay, I'm not showing it anymore. You're asked for the theoretical yield when we cool down a solution containing 1,000 kilograms of sodium sulfate in 5,000 kilograms of water. So I'd like to write it as is where is. I will not write it in the form of concentration. So that way later on you would know how to work your way through it. So it says there you have 1,000 kilograms of solute for 5,000 kilograms water. So I write here initial. This is the initial concentration. So mass is 1,000 kilograms. Our solute is sodium sulfate.
Miss, excuse me.
Yes. You
Miss,
cannot
wait ka
read?
naman, Miss. Kaya naka-share screen.
Okay. Wait. Yes. Where is it? Hey, where are you? Wait, class. It's not sharing here. I thought I am already. You see it?
Okay na, Miss.
Sodium sulfate. And you have mass of water 5,000 kilograms. This is water. Okay, 10 minutes. You'll have the initial concentration, and I like to label that as C sub O would be. Remember, we are to express concentration in terms of, so what did the PowerPoint say? In terms of the formula that we're using, the concentration should be expressed as mass of anhydrous, that means solid only, over mass of solvent. So we were going to deal with the given as is where is. So solid only over that of the solvent. So this is 1,000 over 5,000, and this should be 0.2. Okay, now please check what I'm writing there. I go to the problem. So it says there, the molecular mass of sodium sulfate is 142. So I'd like to place here molecular weight is 142. That's for the sodium sulfate. Okay. Sorry, where is my... Then we have the temperature at 283 Kelvin. So your feed is at a temperature of 283 Kelvin. That's based on the statement. Feed temperature is 283 Kelvin. Then it says that the solubility of sodium sulfate is 9 kilograms anhydrous salt per 100 kilograms water. Now, this phrase class that says the solubility of sodium sulfate is 9 kilograms anhydrous salt per 100 kilograms water tells you that this is already the concentration, final concentration of your solution containing the crystal. So it is 9 per 100 kilograms water. So I'd like to write it that way. So your C, final concentration is 9 kilograms solute or solid per 100 kilograms water. So in this case, 9 divided by 100, that should be 0.09. So I will not anymore write the units. Okay, now I'm already solving the concentration of the given. And then it says there that your crystals will be now in the decahydrate form. So how would you interpret this? Your crystals will be in the decahydrate form. How would you write that? Crystals already in the decahydrate form, meaning your crystals here in the final solution will be sodium sulfate decahydrate. So it's already hydrated. This is the anhydrous salt. This is the hydrated salt. So the molecular weight of this is given to be, how much is that? 322. So this is 322. Hi. What else is given here? It may be assumed that you have 2% of water. It may be assumed that 2% of water will be lost by evaporation. So I'll just write it here so everything will be written here in terms of the given. You have 2% evaporated, so you have E as 0.02. Okay? So the problem is asking you to determine the yield. So it's the yield that is being asked. So we go back here and write required is the yield. So if this is the required, we have to write down the formula for it. So yield is equal to, I'll copy it here, R omega 1 C1 minus C2, wait, 1 minus E. 1 minus E. And then the denominator of this is 1 minus C2 R minus 1. So this is 1 minus C2 R minus 1. So we will substitute what we have. So the R is defined as the ratio. So we'll go back to that part of the slide wherein it's defining what should be the R. So the R is the ratio of the molecular mass of the hydrate over the molecular mass of the anhydrous salt, meaning molecular weight of sodium sulfate decahydrate over molecular weight of only of sodium sulfate. So I'll go back here and solve for the R. So R is molecular weight of sodium sulfate decahydrate over molecular weight of sodium sulfate only. Let's say this is our equation 1. So you have, based on what we have here, 322 over 142. So this is 322 over 142. 342 divided by 142. That should be 2.41. Now, what else do we need? The E is there already. The concentrations I already solved in the given. So all we have to do is substitute. So we will have the yield here equal to the R, 2.41. So you have a 2.41. Omega 1 is the, wait, here, omega 1 is the initial water content. Let me check if I got it right. Omega 1 is the initial and the final masses of the solvent. So I'm right. Omega 1 is water content initial and omega 2 final water content. So we go back here and determine the initial water content. So the initial water content here is 5,000. So that's the purpose of really having to write the raw data. So initially we have 5,000 of water. So we will multiply this by 5,000. Then we have here, what do we have next? We have the C1 and the C2. So our C1, I did not solve for C1 there. The initial concentration is 0.2 and the final concentration is 0.09. So we will place it in here. You have 0.2 minus 0.09. And based on the formula, we have 1 minus E. So this 0.09 will be multiplied to 1 minus 0.02. Our denominator is 1 minus concentration 2. Am I right? Yeah, multiplied to R minus 1. So the R minus 1. So your R is 2.41 minus 1. And you have already the yield. So the unit of the yield, of course, is mass unit. Okay, so you have 2.41 times 5,000. Sorry, I will have first negative 0.09 times 1 minus 0.02. Okay, then we'll add that to 0.2 and we'll multiply that by 2.41 and 5,000. So my numerator is 1347.19 and my denominator will be minus 1 times 0.09 negative 1 plus 1. My denominator is 0.8731. So you have an answer of 1542.996. Our yield is 1,543 kilograms of, what's your yield? Yield crystal is referring to the sodium sulfate decahydrate.